Hello and welcome back. Well, students, in today's class, as you can see, that we'll be doing the chapter structure of atom. We'll be talking about the basic properties of an atom, the constituent particles of an atom, what an atom consists of. Well, before starting with that, first of all, I want to tell you why we need to know the structure of atom. Well, we know that elements, they are made up of only one set of atoms and they have a unique set of properties. When human being they came to know about this thing that there are certain things which are known as elements and they exhibit a unique set of properties, the question which came to their mind, we have got different elements. Are these elements they are made up of different constituent particles? So from there they started this journey and they wanted to see what every matter is made up of. They started dividing matter into smaller parts. Well, atom or atoms, the term which came, it means not further divisible. Atoms means not further divisible. So for a pretty long time, people they thought that atoms, they are the basic constituents and they are not further divisible. That's the smallest particle. But then certain scientists like Chadwick, Goldstein, Thomson, who proposed some subatomic particles like electron, proton and neutron, gave forward their concept that even we have particles which are subatomic. Now the question came to people's mind, or the basic question was, in case an atom consists of these basic particles, then how an atom it basically looks. Then came Thomson's plum pudding model, according to which means the matter was evenly distributed. An atom is spherical, proton and neutron they are spreaded everywhere, and electrons they were embedded. It was also called as watermelon model. But after that, Rutherford carried out an experiment, scintillation experiment, in which he bombarded a gold foil with alpha particles, and this gold foil was surrounded by zinc sulfide screen. Scintillation is the effect of alpha particles. Whenever they strike a zinc sulfide screen, they give a spark, and from that spark we can detect their presence. So Rutherford observed that 90% of the alpha particle they went through the gold foil. That means 90% of an atom is empty space. However, 10% of alpha particle they were deflected. So according to Rutherford's theory, an atom is not something which is hollow. In fact, it has got a heavier part in the center. The center of the gravity of a sphere is always in the center. So according to him, the heavier part of an atom is always in the center and it constitutes of protons and neutrons. And this nucleus is so heavy that even when an alpha particle will strike with it, the alpha particle has to deviate. This nucleus is not going to deviate. From there came the nuclear model. So Rutherford was the first scientist who gave us the nuclear model of an atom. Then there was a student of Rutherford, Neil Bohr, who was conducting this experiment with Rutherford. He had certain serious objections regarding Rutherford's experiment. So from there our 11th standard structure of atom starts. But before moving there, before moving to the drawbacks of Rutherford's model, we'll study about electromagnetic radiations. We'll see what electromagnetic radiations they are, and we'll see some formulas for that. So first I'll tell you what an electromagnetic radiation is. Well, an electromagnetic radiation constitutes of an electrical and a magnetic field which move perpendicular to each other and perpendicular to the direction of propagation. Now suppose this is the direction in which the wave is traveling. You'll have two different waves. Now suppose this is the electrical wave you have got. Perpendicular to this, you will see one more wave moving along with this. I'm shading it so that it will become easier for you to recognize. And suppose this is the magnetic wave. So here you have magnetic wave. So you can see that electrical wave and magnetic wave, they are perpendicular to each other and they are perpendicular to the direction in which they are moving. So all electromagnetic waves, they constitutes of two waves, that is electrical and magnetic wave, which move perpendicular to each other and perpendicular to the direction of propagation. All electromagnetic waves, they have a fixed velocity and we represent it by C, that is 3 into 10 to the power 8 meters per second. It's not exactly 3 into 10 to the power 8 meters, but we round it off and it is 3 into, we take it as 3 into 10 to the power 8 meters per second. So this is the velocity with which all electromagnetic radiations then move. Well, students, a question comes to your mind: Have you seen that electromagnetic radiation or not, or what are the different type of those electromagnetic radiations? So this is what I'm going to tell you. We are going to talk about electromagnetic spectrum. What all different type of electromagnetic radiations we have got? The group of those electromagnetic radiations. But before that, I want to tell you some basic properties of waves. See, here I've got a crust and I've got a trough. The distance between a crust and a trough, this distance, we call it wavelength, and it is represented by lambda. So the distance between a crust and a trough is wavelength and it is represented by a lambda. Likewise, we have another term, we call it frequency. We represent it by nu. Frequency is what? It is number of cycles per second. That's why in frequency you often have dimension second inverse or hertz. So frequency represents the number of cycles per second. By now we have seen wavelength, that is a distance between a crust and a trough. We have seen the number of cycles per second, we call it frequency. The another term we have is a wave number. Wave number again is frequency. It is another method of expressing frequency. It is the number of cycles per meter. So number of cycles per meter is wave number, and wave number is always equal to 1 by lambda. So longer the wavelength, the lesser will be the number of waves per meter. Suppose a wave has got a wavelength of 1 meter, then its wave number is 1. And there is a wave which has got a wavelength of half meter, then the wave number will become 2. So lesser the wavelength, more will be the wave number. So it is 1 upon lambda. Basic wave equation is what? According to the basic wave equation, the velocity of a wave is always equal to product of frequency and wavelength. So in this case, we can say C is equal to nu lambda. C, as I told you earlier, C we can say is the velocity of light, because light again is an electromagnetic radiation. So these are the basic formulas. Now I'll show you different type of electromagnetic radiations. Now suppose here I'm going to show you those radiations. Here I have high frequency and here I have low frequency. Well, all radiations which have got a higher frequency will have higher energy. So we'll see electromagnetic radiation which have very high frequency, and in that we have gamma rays. Gamma rays, they are generally produced by radioactive decay or nuclear disintegration. Whenever you talk about radioactivity, you will talk about gamma radiation. It moves out from the nucleus and they are very highly energized radiations. They have velocity equal to the velocity of light, that is 3 into 10 to the power 8 meters per second. Now, after gamma rays, we have X-rays. X-rays have got slightly lesser energy than gamma rays, but still they have very high energy. Again, since they are electromagnetic radiation, they have the same velocity. After X-rays, we have UV radiation, that is ultraviolet radiation. Ultraviolet radiation, again, if we talk about ultraviolet radiation, you might have heard about large number of ultraviolet radiation or large amount of ultraviolet radiation. It comes from sun. Sun is a major source of ultraviolet radiation. So UV radiation, which is in high quantity, is injurious since it causes skin cancer. So you might have heard about a lot of sunscreen lotions which comes into the market, and in their ads they generally say that it protects you from harmful UV radiation. So it is that UV radiation, and it travels with the velocity of light. After UV radiation, we have visible radiation, in which comes Vibgyor. So all visible radiations, they are also electromagnetic radiation. As far the harmfulness of visible radiation is concerned, we know that it is not harmful unless it is not in the form of laser. So all visible radiation, all visible lights, they also travel with the same velocity, that is 3 into 10 to the power 8 meters per second. After visible light, we have infrared radiation, IR radiation. Infrared radiation, again, it is not visible to us, but there are certain animals, species which can easily detect these infrared radiation, and they generally see through these infrared radiation. Like we talk about snake or mosquito, they sense these infrared radiations. These are the radiations which are generally used in large number of remotes. So they do have the same velocity, that we say the velocity of light, 3 into 10 to the power 8 meters per second. After infrared radiation, we have microwaves. These are the waves in which all mobile communication is done. People, they generally use microwave oven. So if these microwaves, they have got a higher frequency, they are injurious. So after microwaves, the last one is the radio waves. Radio waves are those in which long distance communication is carried out. We control our satellites which are very far off from Earth. Satellites, they communicate with us, they send photographs to us through these radio waves. So radio waves, if we talk about them, they are generally responsible for long distance communication. So this is all about electromagnetic spectrum. These are the different type of electromagnetic radiations you have got. In this, before starting further, I would like to tell you one thing, that energy of a radiation is directly proportional to its frequency. As I have shown you this here also, that the high frequency means high energy, low frequency means low energy. Energy of radiation is directly proportional to frequency. It was postulated by Planck's, who gave us quantum concept. So according to Planck's, the energy of radiation is directly proportional to its frequency. If I remove this proportionality, I had to put a proportionality constant, that is H. So we have got energy of radiation is equal to EH, nu H, where H is the Planck's constant, 6.63 into 10 to the power minus 34 is its value. So this value we are going to use in large number of numericals. Whenever we have to calculate energy from frequency, you will be given frequency and you will be asked the energy of that radiation. So simply you have to multiply it by Planck's constant. So energy of radiation is equal to h nu. And from this formula we can see that nu is equal to c by lambda. So it may also happen that you will be given wavelength and you have been asked the energy. In that case, you will do energy of radiation is equal to h into c by lambda. Now we know the value of h, we know the value of c. Since their value is constant, so their product is also constant. And every time it will come out to be 19.89 into 10 to the power minus 26 by lambda. Mind one thing, that lambda here has to be in meters, because the velocity of light which we have used is 3 into 10 to the power 8 meters per second. So here you got two different formula. The first one is energy of radiation is equal to h nu, where you will calculate the energy through frequency. The second one is E is equal to 19.89 into 10 to the power minus 26 by lambda, where lambda is in meters, and you'll calculate energy through this lambda. So this is how you can calculate energy of a radiation. Now we'll move on to the drawbacks. As I told you earlier that there were certain drawbacks of Rutherford's model. So we'll see drawbacks of Rutherford's model. Drawbacks of Rutherford's model. Well, the first drawback was absorption and emission of electromagnetic radiation by an atom. Well, it is quite evident that an atom has a tendency of absorbing energy and re-emitting energy in the form of electromagnetic radiation. How it happens, Rutherford could not explain it. I give you one example for that. Suppose I have got an iron rod and I am heating this iron rod. If I heat it on burner, it will get hot. Now, why it has got hot? It has got some energy inside where that energy is stored. Every atom has that tendency of storing that energy. So, this iron rod will store some energy inside. If I take it out from that burner, now I'll observe that the radiation is coming out from this iron rod. How come this radiation is now coming out? All atoms, they have a tendency of absorbing and then re-emitting energy in the form of electromagnetic radiation. How it happens, where they store this energy? Rutherford could not explain that. I give you one example for that. You might have heard about greenhouse effect or global warming. What happens, the radiation, it comes from sun in the form of UV. When it comes onto earth, the earth gets hotter. Why it gets hotter? Because it absorbs that radiation. Where it absorbs that radiation? In atoms. It constitutes of large number of atoms. So those atoms, they have a tendency of absorbing energy. And in the night, what happens? Earth re-radiate or it emits that radiation out. Now, how atoms, they have this capability of absorbing energy and then re-emitting energy in the form of electromagnetic radiation. Rutherford could not explain that. The absorption and re-emission of electromagnetic radiation. The second drawback of Rutherford's model was the stability of an atom. Well, if we see, according to Rutherford, an atom is somewhat like this, where you got a nucleus in the center and you have a circular path around the nucleus in which the electron revolve around the nucleus. According to electrodynamics, when a charged body, it moves, it loses energy in the form of electromagnetic radiation. And secondly, the nucleus is also attracting this electron towards itself. So an moving electron should lose energy in the form of electromagnetic radiation. Since nucleus is attracting it, it should come closer to the nucleus and ultimately fall into the nucleus. So an atom should vanish after some time because these electrons, they'll come closer to the nucleus, they'll fall into the nucleus, an atom will vanish. It should vanish. But the law of conservation of matter states that atom can neither be created nor can be destroyed. So when this question was put forward to Rutherford, how come an atom is stable, he could not answer that. He agreed to this fact that a moving electron should lose energy, that moving electron should fall into the nucleus and an atom should vanish after some time. But an atom is stable due to law of conservation of matter. Rutherford could not explain it. Well, who explained this then? These two drawbacks of Rutherford's model were explained by Niels Bohr. And Niels Bohr's, what we call Bohrs model, is not different from Rutherford's model. It is quite a way same as Rutherford's model. The only thing is, the facts which Rutherford could not explain, Niels Bohr explained that. And that too because by the time of Niels Bohr's model, Max Planck gave its quantum concept. So Bohr's used that quantum concept. We can say that Bohr's model is somewhat Rutherford's model plus Max Planck's quantum concept. Max Planck's quantum concept. Well, we know Rutherford's model, according to which an atom consists of centrally placed nucleus containing proton and neutron, and electrons revolving around the nucleus in circular path known as shells. Now we'll see what quantum concept is basically, because if we know the quantum concept, we can combine them together. We'll arrive at the Bohr's model. Well, according to quantum concept, the absorption and emission of energy by an atom is not discrete. It is actually quantized. Discrete means what? An atom or any body cannot simply absorb energy in any multiples and re-emit energy in any value. It's not like that. Because all electromagnetic radiation, they are made up of packet of energy, and those packet of energy are known as quanta. Now suppose energy of one packet is x joule. So a body can absorb x joule, 2x joule, 3x joule, 4x joule, 5x joule. If we think that a body can absorb 1.5 joules, 1.5x joules, that is not possible. Either 1x or 2x or 3x, no fractional. So whatever the energy of one packet is, the energy is always absorbed and re-emitted in the multiple of those energies. So this is what quantum concept is. So according to this concept, all electromagnetic radiations are made up of packet of energy. Those packets are known as quanta. The energy can be absorbed and re-emitted by a body in the multiple of these quantas. So absorption and re-emission of energy is quantized. Niels Bohr used this. Now we'll see Bohr's model. What is Bohr's model? Well, according to Bohr's model, an atom consists of centrally placed nucleus and circular path around the nucleus in which the electrons revolve. But Bohr coined a different term for them. He said they are energy levels. Now here you can assign them some numbers like 1, 2, 3, 4, 5, 6. So according to Bohr, an atom consists of centrally placed nucleus which contains protons and neutrons, and that is the heavier part of an atom. This nucleus is surrounded by circular path in which the electrons revolve around the nucleus, and those circular paths, they are known as energy levels. My dear students, keep in your mind that according to Bohr's, a shell which is closer or an energy level which is closer to the nucleus is a lower energy level, because there the attraction is highest. And this is the rule of chemistry. Wherever there is a higher attraction, there is always lowering of energy. As you move from first shell to second, second to third, third to fourth, the attraction from nucleus decreases, so the energy of the energy level increases. So first shell is lower energy level, second is higher, third is still higher, fourth is still higher. So as you are moving away from the nucleus, the energy of the energy level is increasing. Now suppose this is a hydrogen atom. We take it as hydrogen atom. What Bohr said that an atom consists of centrally placed nucleus. In hydrogen atom, you have got electron in the first shell. And this electron has got some energy. It has got a lesser energy because it is in the first shell, and first shell can accommodate only those electrons which have got lesser energy. So this electron has got a lesser energy. I assign an arbitrary value to this electron. Suppose this electron has got an energy of 1.5 joules. I'm assigning this value arbitrarily. It's not like that it has got an energy of 1.5 joules. I'm just giving you an example. Suppose it has got an energy of 1.5 joule. Now what I'm doing, I'm heating this atom I'm providing some energy by burner. When I'm providing that energy, that electron will absorb that energy. Suppose it has absorbed 8 joules of energy. Its final energy will become 9.5 joules. As I told you that the first shell is a lower energy level. It can accommodate only those electrons which have got a lower energy. Initially, the energy of the electron was 1.5. Now the energy of the electron has become 9.5. And the electron which has got 9.5 energy cannot be accommodated in the first shell. If first shell cannot accommodate an electron of 9.5 joules, there is definitely some other shell which can accommodate it. Because I told you this thing that as we move away from the nucleus, the energy of the energy level increases. Suppose, again, we are just considering it. Suppose it is the fifth shell that can accommodate an electron of 9.5 kilojoule. So what will happen? This electron will jump from first shell to ninth shell. Because now it has got an energy of 9.5 kilojoule and first shell cannot accommodate it. It is only the ninth shell that can accommodate electron of higher energy. Because as we move away from the nucleus, the attraction decreases, so the energy of the energy level increases. So it is the fifth shell which is accommodating it. So what will happen? The electron will jump from lower energy to higher energy. This electron is not stable at higher energy because the nucleus is continuously attracting this electron. So this electron will move back from high energy to low energy. So whatever energy it has absorbed, it will radiate it. So that will come out in the form of electromagnetic radiation. This is how Niels Bohr explained the absorption and emission of electromagnetic radiation by an atom. When, again, we'll come to the same example. Suppose this is an iron rod. When I'm heating this iron rod, the electrons, they are absorbing energy. They are jumping from lower energy level to higher energy level. But when I take it out from the burner, the electrons now moving from higher energy level to lower energy level. And whatever energy they have absorbed, they are losing that energy in the form of electromagnetic radiation. So this is what happens in an atom. If you want to calculate the energy of this electromagnetic radiation, we can simply write it is equal to E2 minus E1, where E2 is the energy of higher energy level and E1 is the energy of the lower energy level. If I tell you a formula of calculating energy of energy level, you can easily calculate the energy of higher energy level and the energy of lower energy level. From the energy of higher energy level, you will subtract the energy of lower energy level and you will get that difference, which will be the energy of the radiation. My dear students, here in this case, E2 never means energy of second shell and E1 never means energy of first shell. E2 means energy of higher energy level. So whatever will be the higher value, that will be E2, and whatever will be the lower value, that will be E1. Now the question comes, how to calculate energy of an energy level? Well, according to Bohr, the energy of an energy level can be calculated by a formula that is minus 2 pi square m e to the power 4 into z square by n square into h square. The dimension is joule per atom. We know the value of pi, we know the mass of electron, that is 9.1 into 10 to the power minus 31 kg. We know the charge on electron, that is 1.6 into 10 to the power minus 19 coulombs. Atomic number of different atoms will be different. So it is different, it is variable. We know the value of Planck's constant. I told you 6.63 into 10 to the power minus 34. So keeping all these constant values, this formula comes out to be energy of nth shell is equal to minus 2.18 into 10 to the power minus 18 into z square upon n square, joule per atom, where z is the atomic number and n is the number of shell. Whatever shell whose energy you are trying to calculate, the number of that shell. Now we'll move on to this formula, that is energy of radiation. I'll write this. So energy of radiation, we know it is E2 minus E1. So in this case, it will become minus 2.18 into 10 to the power minus 18 into z square upon n2 square minus 2.18 into 10 to the power minus 18 into z square upon n1 square. Now, since we have got a negative sign outside this bracket, the sign will change inside. It will become positive value. So it will become 2.18 into 10 to the power minus 18 into z square upon n1 square minus 2.18 into 10 to the power minus 18 into z square upon n2 square. Again, the dimension is joule per atom. Now I'll take out the common terms. So energy of radiation is 2.18 into 10 to the power minus 18 into z square into 1 upon n1 square minus 1 upon n2 square. The final formula comes out. Energy of radiation is 2.18 into 10 to the power minus 18 into z square, where z is the atomic number, n2 square minus n1 square upon n1 square into n2 square, joule per atom. So this is how you can calculate energy. Many times questions they are given to you, like in a hydrogen atom, the electron from the first shell has jumped to the fourth shell. Now this electron, when it is returning back, it is coming to the second shell. From fourth shell, it is coming to the second shell. Calculate the energy of the radiation that is coming out. So you have to calculate this part. Here in this case, N2 will be 4 and N1 will be 2. So you'll put these values in the above mentioned formula and you'll calculate energy of radiation. It is not only that energy of radiation will be asked, many times frequency and wavelength they are asked. For that I have already told you the formula. First you will calculate energy from air, then you know energy of radiation is equal to h nu. From here you can calculate frequency. You also know energy of radiation is equal to 19.89 into 10 to the power minus 26 by lambda in meters. So this is what you can calculate. So this is how Niels Bohr explained the absorption and re-emission of energy by an atom. This is what we have for today's class. In next class, I'll tell you the agenda for the next class. In next class, we'll be talking about quantum numbers. We'll talk about hydrogen spectrum. We'll talk about quantum numbers, emission lines, Pauli's exclusion principle, Hund's rule of multiplicity, Bohr's principle. This is what we are going to do in the next class. So please be connected and please go through these formulas, do a lot of numericals. You have any doubt anywhere, you are always most welcome to ask your doubts. You can send me a message for that. The number is already flashing on the screen. And I request you to subscribe this channel so that you will get all the notifications on time. This is all about this class. Thank you very much. Thanks for joining.